Well, good afternoon. Welcome to Issues in Environmental Science for the 13th of October. And today we'll be covering, share my screen here. So today we'll be covering material based on Chapter 7 of Hasenzal, the Environment textbook. And we'll be looking at specific topics brought up in that chapter, and then I'll be expanding some of that discussion with other information materials. There'll only be one lecture this week because on Thursday we'll be taking the midterm exam during the class period. And so this will be an online exam. It'll be given for all the students during that period of when we normally would be having a lecture and team work. Instead, you'll be answering the questions online as individuals on quizzes similar to the quizzes that you've been taking on a weekly basis. There are going to be two parts to this exam. The part A, which is what we'll do during the 75-minute regular class period, will be 100 questions from the reading quizzes and from my lectures. And you'll have 75 minutes to complete those questions. Part B will be 10 essay and diagramming questions. They'll also be taken from the weekly team questions that you've been answering as essays, and then also from my lectures. These questions or this material will be submitted by file upload, and they'll be, so the files will have to be typed so that they can be read by Turnitin, and Turnitin will be used to check for plagiarism, both for looking at possible online sources of information and by comparison to answers provided by other students. So be very careful to use only your own work and your own wording in those answers for the 10 essay questions. If you do want to use quotations or material that might flag Turnitin, be careful to put it in quotes or otherwise attribute the sources that you're taking it from. And that's fine if you do that, as long as you attribute those sources. So today in class will be, oops, that's not the right question. Today in class we'll be looking at water pollution and air pollution. I'm going to lecture for somewhat longer than I usually do because we'll only have one opportunity to cover the material from Chapter 7 and sort of water pollution, air pollution, human toxicology. So my lecture material will take up somewhat longer than it usually does because the Thursday session will be taken up by the exam. In our breakout session, however, I want to make sure that you discuss as a team the concept of externality, that you understand negative versus positive externality, and that you come up with some examples of negative externality for air, water, and climate. And then for discussion, when we get back together, I'd like you to consider, so we're talking today in lecture about pollution, pollutants, human effects, and so forth. And of course, we can't escape from thinking about our present predicament in terms of the coronavirus pandemic. And just as a thinking exercise, a thought exercise in this, I think it's important to try to understand whether this can be, how we should think about a pandemic. Is it the same as pollution, or is it different from a pollution? Can we gain anything by applying the techniques and the concepts for pollution and pollution abatement to understanding how to control pandemics and pandemic abatement? Let me pause my sharing. I need to make sure, yes, we are recording, okay.
Excuse me?
Yes, go ahead.
So for part B of the exam, like when you mentioned citations and things, would you like us to provide just a works cited at the end of all of the questions and have in-text citations for the individual questions?
Yes, that'd work great.
Okay, thank you.
And I'm not expecting sort of term paper style, multiple citations, but if you do make some statements you do need to tell us where you're getting that. And that's particularly the case if you're quoting or using material that you're getting from external sources to answer your question. Yeah, Berta, go ahead.
And continuing with that question, I just wanted to ask if there's a certain format that you would like our citations in, or just whatever we feel more
Author date. No, you're not being graded on formatting these things,
Okay.
just as long as we can figure out where you got it unambiguously.
Thank you.
Other questions? Okay, so let's think a little bit about environmental health. There's a lot of material packed into this chapter, and I've expanded it a bit to cover more details about different types of pollution and different types of pollution effects. But let's get some vocabulary clear as we proceed with our discussion. So pollution is any unwanted presence in the environment. And that can include compounds, that can also include changes in, so pollution could be a physical effect, some physical presence could be considered a pollution. Most often, however, we consider pollutants to be things which interfere with the normal processes either of an ecosystem or of a species or an individual. And these are often caused by contaminants, something which renders and what's a contaminant? We could define contaminants as a compound or a chemical or a presence which renders a resource unusable. For example, if we pour arsenic into the water supply, we're contaminating it, and because it's no longer fit for the intended purpose. Anything is considered toxic, which is poisonous to people or to animals. And when we think about toxic, we have to think about lethal versus sublethal effects. So a lethal toxicant is something which can cause death. And there are many examples of lethal toxicants. Novichok, the nerve gas agent that has been used by Russian malefactors to poison dissidents, is an example of a lethal contaminant, highly lethal contaminant. But sublethal contaminants are also particularly important because they can accumulate. Their effect may not be immediately noticeable, but they can have very deleterious effects on human health or organism health over time. A particular sort of a toxin is a carcinogen. Carcinogens are very common in sort of pollution effects. So, and carcinogens are examples of sublethal effects, which over time can produce mortality and morbidity. Synergism is an interaction between two or more substances in which the combined effect of putting these substances together can be more lethal than the two individual. The sum is greater than the individual parts. And then in terms of where pollution comes from, we can think about point sources versus non-point sources or area sources. So a point source is a contaminant which can be traced to a particular point of origin, for example, a pipe or a chimney or a runoff, whereas a non-point or area source is diffused from that origin, so it's hard to pin down where it's coming from. An example of a non-point source pollution could be the runoff from parking lots, which causes hydrocarbons to enter into the water supply. The definition or the distinction between point sources and non-point sources can be somewhat fuzzy, but generally speaking, a point source, if a point source can be identified, that might make it possible for authorities to regulate or punish polluters. Okay, so continuing with our sort of concept, we measure pollutants. Very often pollutants are present in trace amounts, and so we have to use very small units of measure to describe the load of pollutants which is being presented. And so very often extremely small measurements are given in parts per million, and parts per million can be by unit volume or by weight. Most often it's by weight. And so ppm is the abbreviation for parts per million, ppb, parts per billion, ppt, parts per trillion. And the fact that we have these numbers, parts per million, parts per billion, even parts per trillion, indicates that some pollutants can have a deleterious, a pollutant effect in very, very small concentrations. Be careful when you're thinking about percentages, because percentages, when referred to pollutants, are rare, because typically pollutants are present in relatively low concentrations. So be careful when you read decimal percents. So like 1.01% is 1/100th of 1%. So you have to be a little bit careful with your decimal points if you're using percentages, and that's why parts per million, parts per billion are the more common.
I have a question, Dr. McDonald.
Yes.
So even though it's called parts per million, I see in your last bullet, it's actually like some examples is like 1 milligram per kilogram. So it's only like 1/1000th, not actually like 1 part per million. It's like 1 part per 1,000.
No,
But
because there are 1,000 grams in a kilogram, and 1 milligram is 1,000th of a gram. So 1,000th of a
oh
pound.
wait, yeah, that was a big mistake on my part. I'm sorry. That's why I was confused. I did the conversion wrong.
Okay, no worries. Yeah, you do have to be careful about that. And that, I've made that exact same mistake. So when you're looking at these things, it's a good idea to, to sort of keep clear in your mind what the units are and how they subdivide. But yes, 1 milligram per kilogram is and 1 milliliter per liter would be a 1 ppm. Okay. So those are pollutants, and when we think about the impact of pollutants, we think about its toxic effect, and there are several different kinds of toxic effects. Acute toxicity are adverse effects which occur very rapidly in a short period of time. And this is, would also be referred to as poisoning. So when the Russian dissident received that dose of Novichok in the water bottle, he experienced an acute toxicity event. So he got dosed with this nerve agent, and almost immediately on the flight experienced what would have been a life-ending illness response to the toxicant, and had to be hospitalized and very nearly died. So that's an example of acute toxicity. And there, in pollution, it's relatively rare to have pollutants which cause those kinds of effects, those kind of sudden onset health effects. More common are chronic toxicities, and these are adverse effects that occur over a period of time after exposure. So that prolonged exposure to a toxin damages cells or organs. And this often takes the place of cancer. So we think about smoking as an activity which can have chronic toxicity. Well, you can smoke a cigarette, and if you're used to smoking, you won't experience any acute effect. But over time, the accumulation of nicotine and tars in the lungs and other parts of the body can cause prolonged effects. And these compounds can be carcinogenic. They can produce cancers and other adverse health effects. We study all this through the science of epidemiology, and the term epidemiology has a lot of currency in the present. We're working with infectious disease experts and epidemiologists who are trying to understand the spread and control of the coronavirus, COVID-19. So epidemiologists are very much concerned with how diseases or how pathogens affect populations as a whole. So they look at, an epidemiological effect very often occurs in small amounts of the population. I don't have a slide to illustrate this, but very often, 1 death in 100,000, change between 1 death in 100,000 and 5 or 6 deaths in 100,000, which seems like a small change in mortality, would actually be something that an epidemiologist would take note of. So small changes in the impact of pollutant or disease on a population can often be a signal that something is wrong. And epidemiologists have the task of trying to detect these kinds of impacts and effects, so that if we see pollution changes, if there's some plant which is emitting some kind of a toxic compound into the air or the water, and then over time we see a change in the mortality rate per 1,000 or per 100,000 of a few individuals, that could indicate that there's been a serious decline in the health of the environment and may signal that some action is needed, urgent action. So epidemiological epidemiology is concerned very often with detecting small changes in health. Some things that epidemiologists and toxicologists do are to look at dose levels. And so rats, fishes, flies, and insects are often exposed to various levels of chemicals to see if they develop cancer or some other kind of deleterious effect. Sometimes these sorts of studies can be difficult to extrapolate to human beings. Other times it's more easily done. And epidemiologists are, looking often at historic exposures to groups of human beings to different kinds of compounds, and looking to see how present-day mortality or morbidity relates to what's been observed in the past. And an example would be to see if an exposed group, a group which is being exposed to a certain carcinogen or other potential pollutants, is experiencing a changed cancer rate. And there are a number of different agencies that look at this. And again, these agencies have received a lot of currency in the press. So the Center for Disease Control, CDC, has been in the news an awful lot because of the pandemic, and they've been quite controversial in terms of what kinds of credence we give to the guidance and advice that the CDC gives. That's something which has become political in today's world. And likewise, the World Health Organization, which has the responsibility, some of the similar responsibility that the CDC has in the United States, the World Health Organization, acting through the United Nations, tries to exercise over the world at large. And in both cases, the disruption caused by the coronavirus has brought into question the ability of these sorts of agencies to provide scientific advice free from political influence. So how do we identify toxic compounds? Well, this idea of dosing rats or experimental organisms, or looking at the probable dosage that human populations are receiving and trying to determine what their effect is, gives us a sort of clue in how to identify toxic substances. There are a couple of terms that we'll throw around. LD50 and ED50 are two terms. The 50 in this case corresponds to the percentage of organisms or test organisms which show a response. In this case, lethality would be the response. So a lethal dose, and here are a variety of compounds which have potentially lethal doses for test organisms, or indeed for human beings if they were test organisms. So aspirin has an LD50. In other words, it will kill 50% of the test organisms if exposed to a concentration of 1,750 milligrams per kilogram. So 1,750 milligrams per kilogram, in this case, administered orally to rats, that would be a dosage of how many ppm?
So would this also mean that 50% of the organisms live even though they get the dose?
Yes.
Okay, thank you.
Yeah. So 1,750 would be how many ppm? 1,750 milligrams per kilogram would be 1,750 ppm. So these dosages are being expressed here in milligrams per kilogram, but that could be interchanged with ppm. So caffeine, 200 milligrams per kilogram is enough caffeine to promote a lethal dose in rats. So caffeine is relatively toxic. It's not much less toxic, interestingly, than heroin. So it's something to think about when you enjoy your morning coffee or your morning tea. And there are other compounds along here. So you get the general idea. Nicotine, look at how toxic nicotine is. Of course, when you're smoking a cigarette or other, chewing tobacco to absorb nicotine, you're getting tiny amounts of it. But it is a very powerful drug with a powerful effect here. Okay, questions on that, identifying toxic substances. These are toxins, things that have produce a deleterious or pathological effect on human beings or test organisms. We can also see what an effective dose is to, and an effective dose is different from a lethal dose, because an effective dose can be the amount of a drug or vitamin or other compound which produces a beneficial effect. And so one of the ways that we're interested in measuring, for example, the effectiveness of a vaccine is whether it would prevent infection with the COVID virus among 50% of the subjects who received the vaccine. So the ED50 for the eventual COVID vaccine is going to be an important measure of whether or not the vaccine is effective. And the LD, and then the rate of what would indicate that a vaccine, for example, was not safe and effective is if it was producing some level of mortality among the test subjects. So I just read in the newspaper that Johnson & Johnson had to suspend their trials of a potential vaccine because among the thousands of people who were getting the test vaccine, 1 or 2 people developed a reaction which they thought might be cued by or might have been caused by the vaccine. So they suspended the test and are proceeding and doubling back to make sure that they understand what was causing this effect in the test subjects who were hopefully responding well otherwise to the vaccine. So ED50 is the effective dose in 50% of the test organisms. And so ED50 causes 50% of the population to exhibit whatever effect is under study. So in the case of a vaccine, the effect is immunity to a coronavirus. And these sorts of responses, however, we're presenting them as 50 and so forth. Typically, they don't work in a strictly linear fashion. More often, the dose response takes place according to some exponential effect. And so these are dose response curves. In this case, we're looking for a toxic response, so an LD50. And the LD50 in this case is marked by this position within the dose response curve. Well, if you look at this curve, what you see here is that very often the LD50 is a sort of a tricky number to arrive at. And because it's on the very steep, the exponential part of this curve. So, a slight change in the dosage level could cause a much higher proportion of the population, or a slight increase in dosage could cause a much higher percentage of the population to exhibit the effect.
What is the reasoning that they only look into like the 50% of like the population? Like wouldn't it make more sense to look and see like which is like more effective for like the majority of population?
Well, the reason is explained precisely in the shape of this curve. So we think that most of the time dose response is an exponential effect. So there's at some low dosage there's no effect, and then at some threshold level the organism starts to experience an effect from the material that it's being dosed with. That effect increases rapidly in this exponential rate, and eventually there's some tapering off point. If you're getting a lethal dose of arsenic, eating a couple of ounces is not much different from eating a pound. if you get my meaning. So the LD50 tries to locate the exact midpoint, of this exponential rate of response. Does that make sense?
Yeah, but like say that like we're trying to find the ED50 for like medicine, like in like actual like practice, we wouldn't just use the amount that's the ED50, right? Like we would use more, or would using more than the ED50 like have bad result?
Well, in the case of prevention, for the vaccine, we can say that they've achieved, they've sort of found this midpoint on the curve. But this, this is, if you took this curve and you looked at it and expressed it not as a exponential rate of growth, but as a Gaussian curve, you'd find that this midpoint fell right into the middle, the top of the bell curve. And so that's the sort of sweet spot where you're getting the greatest effect. And so that's why the LD50 is used. Maybe I could break down. So if you took this same, let's see if I can draw on this page with my pen. Yeah, so if we were expressing this not as an exponential curve, but as a response, so let's see, is it drawing? There it goes. So a Gaussian, you all know what a Gaussian, a bell curve would have this kind of effect with long tails. Oops, it's not. So that would be the percentage of the population affected with this. And so, hitting this LD50 sort of gets you into this, this top of the bell curve. Does that make sense?
Yeah, so like vaccines will really only be 50% effective for any given population.
Well, it's not that they'll only be 50% effective, but if they are at least 50% effective, that means that you're in this portion of the response where the most benefit will occur.
Okay, that makes sense. Thank you.
All right, and but the shape of this curve and the way this increases can differ among different compounds. So it might be more steep than others. And so, these are, LD50s for compound A is much relatively higher than for compound B. So you can have two compounds that have, very different LD50s. So that the dose response, has a more gentle slope for toxicant B than it does for toxicant A. Okay? And another thing which is not shown in this graph and isn't discussed in the book is that stressors or insults from environmental contamination can often be cumulative in their effect. So, people who have underlying conditions or who are exposed to multiple different pollutants can, start to experience, extreme health effects, because of a collection of different pollutions and different toxicants that they're exposed to.
Are there any studies that take into effect populations that have certain immunities to, like, say, Sherpas, in the Himalayas that, that have the ability to, not require as much oxygen? I mean, are there any
Well, a well-designed,
loopholes in this, or?
Yeah, absolutely, Darren. Well, a well-designed study, an experimental curve, is going to use a test population in which those sorts of effects are normalized out. So, if you were trying to measure, the impact for all, and that's one thing that, for example, the coronavirus testing is trying to do, is they want to make sure in testing this vaccine that they have a good mixture of men, women, different ethnic groups, age groups, and so forth, because you want to make sure that there isn't one group which is going to respond particularly well or another group which is not going to experience the benefits. So that statistically you want to get a broad enough and most representative enough sample so that you're not looking at some kind of artificial effect of a particular characteristic of one group or another. So yeah, if you were measuring you know, how people respond to low pulse oxygen, you probably wouldn't want to have Sherpas in there because they're popular, or not Sherpas, but you know, people from Tibet or people from living in the Andes Mountains, where they're adapted to chronically low levels of oxygen, and they have specific sorts of physiological responses, physiological adaptations. So you wouldn't want them in your test group if you were trying to look at a more general impact for human beings. Okay.
Okay. Thank you.
So, oops, I wanna get in there. So, you know, very often, as I was saying, that there can be a mixture of different compounds or different contaminants that are affecting the health or the well-being of a human population or a wildlife population. Let me see if I can get rid of this. There we go. So adverse mixtures are where each effect adds on to produce a response. And so, you know, that's kind of like the progress along the growth curve, where you're increasing the dose. So an additive effect, if you're adding different contaminants, the effect of different contaminants together, it's, you know, it's sort of steadily moving you along that dose response curve. Synergistic effects mean that the mixture results in a much greater response than the components of the parts. Antagonistic effects could result in smaller responses. So a synergistic effect of different pollutants being added together would be a bad outcome. It would make it worse. Whereas an antagonistic effect might be that the different compounds were offsetting each other. And very often it's difficult or impossible to test all combinations. And so particularly in experiments, toxicological experiments, it's necessary to normalize out individual compounds and try to you know, limit the dose and the impact so that in analyzing the results, you can tell specifically how the effects were caused. Okay, so that's a little primer on toxicology, very brief primer on toxicology, epidemiology, and some of the terms that we use in describing pollutants and environmental effects. And now let's look at air pollution and water pollution. Again, relatively brief examples, but these bring out different, you know, these air pollution and water pollution are what we think of most often when we think of pollution in the human environment. And so let's consider, and they have different effects in different ways that they're presented. So let's consider air pollution first. So air pollutants are caused by gases or by particulates. And so gases are compounds like oxygen or ozone or nitrous oxide that are present in the environment, and they mix with the atmosphere freely. They may be heavier or lighter, but they're behaving as fluids and mixing fully. Particulates are tiny particles, so they're not in gaseous state. They remain in solid phase, but they're small enough so that they're suspended in the air and can be absorbed or otherwise presented for an effect. And again, the pandemic gives us examples of the nature of particulates. And so, you know, one of the concerns about transmission of COVID is that it can occur through droplets. In other words, as I'm speaking, you don't, fortunately, you're not appreciating this, but as I'm speaking, I'm expelling tiny droplets of moisture with my voice. And those droplets, most of them, the heavier ones, the larger ones, are settling out fairly quickly. And so, you know, that's where the 6 foot of social distance, you know, provides a reliable measure of protection. But much, much smaller particles can also circulate and travel much farther. So a typical virus particle is 1/10 of a milligram of a micron in diameter. So that's a very tiny particle. And at 1/10 of a micron, that's smaller than a typical particle of water condensation. Or smoke particles. So if you think about, how a very small particle can be suspended in the air and travel considerable distances, that gives us a indication of why we need to be concerned with particulates. So there can be natural sources. For example, volcanic particulates, gases, and smoke is something that's getting a lot of attention. Or they can be anthropogenic, soot and smog. Natural sources probably account for more overall air pollution than human sources do, but human sources tend to be concentrated and chronic and thus can pose a greater human health effect. So there are many sources, many natural sources of air pollution, but they tend to be sort of more broadcast. They can be, in the case of the California fires, which we'll look at momentarily, they can be concentrated. Okay, so that's that sort of defines air pollution for what we want. Air pollution has got a long history. Soot particles have been found in archaeological remains. So we've found particles of soot and particles, skeletal indications of lead contamination in archaeological findings from, hundreds or even thousands of years ago to indicate that airborne pollution has always been or has a problem for human health. Stepping ahead, when people began using coal as a source of fuel, very quickly the heavy smoke that was produced by burning coal created pollution effects. And these were noted, all the way back, in the 1500s, 1600s, there were actually laws on effect to stop people burning coal in certain places. These tended to get swept aside as the Industrial Revolution took force and people began living in larger and larger urban settings. And so by the 19th century, all the way into the 1950s, the use of coal as a source of fuel for heating, for electrical generation, had created a sort of a chronic pollution effect. And London was known for its pea soup fogs. You've probably seen that, you may have seen that in the literature or books. They talk about the London fog. Well, the London fogs, really reached came to the attention of authorities when there was a temperature inversion in the 1950s that really trapped the smoke and the other material largely from coal sources. And the effect was that there were about 4,000 deaths, particularly among old people. And so that really caught the attention of authorities and was the beginning of a sense that they really had to take action to remove coal. In 1997, there were fires in Indonesia, which caused widespread effects. There was something called the Asian brown cloud in the early 2000s. The Asian brown cloud was particularly affected by coal-fired power plants and other sorts of burning, fuel burning in India and China, where coal has been and continues to be an important fuel source. So particulates are a particular effect. And then in 2018, 2020, present day, the Western fire season has produced air pollution, air quality standards that have been very concerning. And so we can think of, and I've already sort of covered this, primary pollution and secondary pollution. So primary are emitted directly into the air. Examples include carbon dioxide, particulates, carbon dioxide, hydrocarbons, nitrous oxides and sulfur oxides, so-called NOx and SOx compounds, and volatile organics. Volatile organics would be the sort of aromatic compounds that you would notice from hydrocarbon pollution, for example. There can be secondary pollutants, which are caused by reactions between primary pollutants within the atmosphere, and I'll show you some examples of that. Two examples are photochemical smog and acid rain. I don't have a slide about acid rain. Acid rain has been a problem, but acid rain is caused by a combination of sulfur oxides that combine or dissociate to produce weak acids that then fall as part of rain and snow, and those acids can change the pH, can lower the pH of lakes and rivers, and can have a very deleterious effect on aquatic organisms and on plants and animals that depend or that are affected by acidified rains. All right, well, let's look at some of the health effects and how this is caused and how this the health effects of air pollution can be very serious and very expensive. And so here's an estimate in the cost for billions of dollars per year for different kinds of or different effects. So premature deaths, which have been rising steadily, cause in the order of 20 or 30 billion dollars per year of damages. Chronic bronchitis, restricted activity, other symptoms, these are all effects which can be broken out individually and measured individually. But if you look at the overall impact in terms of an economic measure of how these pollutants affect, you can see that all of the things add together to create a more serious effect. So air pollution can affect the human body in a number of ways: the eyes, the nasal cavity, windpipe, and particularly the lungs are sensitive to impacts from air pollution. And then if we look at sort of, air quality, and we'll look at air quality in a second here, air quality is measured as a combination of a bunch of different kinds of pollutants. And so the AQI, Air Quality Index, categorizes air quality in terms of all these different possible air pollutants. So there's PM10 and PM2.5. PM10 and PM2.5 are important metrics. These are the particulate matter, and the 10 refers to the size or the average size of the particles. So PM10 are particulates that have an average size of about 10 microns, and PM2.5 are particles that have a size of about 2.5 compounds. And so, if you just look down the list here, as the concentration of these particles increases, and this is per cubic meter of air, when you start getting up into, the hundreds, that's a very poor, severe effect. Nitrous oxide has got different levels of dosage. Ozone, carbon monoxide, sulfur oxide, nitrous oxide, and lead are all different examples of effects. All right, and particulate pollution, the large particles, matter less than 10 microns, are of particular concern. So this is looking at a range of sizes from very tiny particles up into very large particles. So beach sand, human hair are sort of up in this size. Pollen, which affects me and everybody else around here. These are pollen grains, tend to be larger than 10 microns. And so you can see the range here. So the greatest lung damage occurs in this 0.1 to 10 micron particle size range. And very fine particles, those less than 2.5 microns, also pose unique risks because they are so hard to get rid of, and they can be so pervasive. Well, this graph here shows you on the lower part of the screen here, shows you sort of changes in average particulate matter emissions. These are expressed in metric tons in the US over time. And you can see that in the 40s and 50s, we were experiencing a lot of air pollution. And then this began to decline, particularly in the 60s, and then very sharply in the 70s. Well, what happened in 1970 was that the Clean Air Act was passed, and this is a comprehensive federal law that regulates all sources of air emissions. And so the auspices of the Clean Air Act included, many of the compounds that I previously discussed: smoke, soot particles, nitrous oxide, hydrocarbon pollution, etc. So the Environmental Protection Agency has established standards for all of these many compounds, and by setting limits on emissions and emitters, they've brought those factors under control. So there has been a marked improvement in air quality since the Clean Air Act was enacted in 1970. You can see that very graphically in this table here. Things are changing, however. The current administration has been actively moving to change the auspices and the way in which the Clean Air Act is interpreted and enforced. So on the 20th of June, citing the economic impact of the corona pandemic, President Trump signed an executive order that calls on agencies to waive required environmental reviews of infrastructure projects built during the pandemic-driven economic crisis. So that refers specifically to industrial plants, to pipelines, and so forth that are potentially or emitting pollutants into the air, and would have received prior to this executive order more strict review and control under the Clean Air Act, but with the executive order, these regulations are waived or weakened. And at the same time, the Environmental Protection Agency under the new administration the present administration has proposed a new rule that uses cost-benefit analysis to enact clean air regulation. And so that limits the strength of future pollution controls. So the Clean Water Act, the Clean Air Act, these are laws, and they have produced positive effects over time, but none of these laws are set in stone, and they are subject to changing political circumstances. All right, well, let's look at, yes,
So, I had a quick question. So are our current levels now higher than, what is that, 2000 at the end of that graph? Are we higher now than where that was?
Well, I was gonna get to that.
Oh, sorry.
Yeah, we are higher. Well, locally we're higher. So this is a map, a global air quality map. I'm going to change the screen here. So this is a map, and this is showing you air quality, and this scale on the lower screen is that same scale that I showed in the previous AQI index there. And this is air quality measured at different points around the world. And let me stop sharing this screen, share a different screen, which takes us to the real-time map. So here's that screen, and we can zoom in on that. And here we can see that the previous map showed us that there were a lot of different places where there was poor air quality, but there's a lot of poor air right now in California, despite the fact that California has had and has very strict air pollution controls. And so, one of the California and particularly Los Angeles was very heavily impacted by smog and air pollution. And their response to that was to try to bring into effect air quality and air pollution controls. And that was, central, instrumental in the formulation of the Clean Air Act. However, the present day has produced very poor air quality. The poor air quality is not located near the city. So here's Los Angeles, here's the Bay Area. And this is today, I brought up this map today. So you can see that, they are in the orange zone. I have my sister, two of my sisters and my parents live in the Bay Area. And so I was talking to my sister on the phone the other night. And she's saying it's been great because they've had a lot of rain and onshore winds, and that sort of cleared out all of the smoke. Well, if you look at this map and sort of hold this picture of California in mind, and then we go to a different screen. Let's see if I can find that.
Professor?
Yes.
I have a quick question, and it's about, it's just about like the Clean Air Act and like the regulations on like present day.
Yeah.
I really thought that NOAA, National Oceanic Atmospheric Administration, was run by or regulated by the EPA. But I just found out it's actually regulated by the Secretary of Commerce. And do you think maybe that switch, I think I was reading that in Nixon's presidency, I think he made, he moved NOAA or moved that administration. And so I was just wondering, do you think that change maybe had caused,
Well, no, okay, so you're talking about agencies
Yeah.
and what part of the government are they, what agency are they part of? And so the parent agency for EPA is a cabinet level appointment. And the Department of Commerce is a cabinet, so the Commerce Secretary is a cabinet member. Okay? NOAA sits under the Department of Commerce and has been there for I think practically since it was created. And it's not a perfect fit in the Department of Commerce, but it's there because of its importance for it's placed under the Department of Commerce because of its importance, the importance of air and water quality for climate and weather on the ability or the effectiveness of commerce. So that's why it's placed there. EPA was created as a cabinet level agency. And so, there's been a lot of discussion. One of the things that, Governor Perry, wanted to do was to abolish the EPA. And so there've been moves to try to move that. But I think that NOAA, and in particular, has more of a sort of a less of a regulatory role than the EPA does. So NOAA is a science agency, a fact-based organization, not really an agency. And so they're, modeling, investigating, measuring impacts in the about the oceans and the atmosphere, and trying to determine how those are going to affect weather and currents and hurricanes, etc. Whereas the EPA is, specifically charged with protecting the environment and enforcing such laws as Congress enacts, for that purpose. So I get what you're saying, but I don't think that that's a specific cause of, changes in the way in which EPA is able to regulate. But, back to the question of California, here we can see, if you looked at that previous screen, here you can see that, the places where there were poor air quality, are in the eastern portion of the state, exactly where these very large fires are burning. So the fires and the particulate smoke and the, and the compounds in the fire, not just the particulate matter in itself, but the hydrocarbons, and other compounds, arsenics and other compounds in the smoke, has a potentially very harmful health impact. And I worry a lot about my elderly parents, who can't go outside, and my sister and her daughter who have to stay inside, when there are these bad fire days. So air pollution, in this case, it's air pollution caused by these natural fire events, even though they're related indirectly to forest management, but also to climate change effects. Okay, so let me go back to, so that was just by way of saying that these pollution events, these air pollution pollution events can result from natural processes, and they can be just as deleterious as from anthropogenic pollutant sources. Okay, let me talk briefly about specific compounds. I'll try to get through all this, and I'll go back to my slide here, stop sharing, share. Okay, so just running through a couple of the different compounds, sulfur dioxide and sulfur, and all of these compounds that I'm going to talk about are currently regulated by the EPA, colorless and odorless. Sources of sulfur dioxide come from burning coal and other fossil fuels. It's been associated with chronic respiratory diseases, increased bronchitis, causes decreases in lung function, irritation, hyplasia, mucus secreting. It also produces a secondary form of pollution in the effect of acid rain. And sulfur dioxide is also a component in photochemical smog. So this is the way that we develop concentrated releases, burn or oil or coal in an urban area. This creates sulfur dioxide, which mix with particulates. And when there's stagnant, stable air, relative humidity, it can get an inversion layer. You get these thick smogs. And this is a concentrated sulfurous smog. And this is exactly the sort of London pea soup fog that caused damages. It's the same sort of smog which used to really affect the air quality in Los Angeles. Another compound are nitrous oxides, so there can be multiple different forms: nitrous oxygen, nitrous oxide, and so they're given this NOx abbreviation. You can do the same thing with sulfur compounds. So if you hear about NOx or SOx compounds, that's what folks are talking about. These can be major throat and lung irritants. The sources include automobiles, power plants. Nitrous oxide does have the other impact of destroying ozone in the other atmosphere, and it interacts with hydrocarbons to produce photochemical smog in urban air. Well, what's photochemical smog? Photochemical smog happens when you mix sulfur dioxide or sulfur oxides and nitrogen oxides along with hydrocarbons. And so how would you get that? So, hydrocarbons are, and then all these compounds interact in, with the presence of sunlight. And so you get this sort of time series of events, and you can sort of see what's happening here is that, as people start, and this is, concentrations of photochemical smog from a hypothetical day in Los Angeles, whereas people start commuting to work, there's a lot of release of nitrous oxides from automobiles, and then they start reacting with sunlight that produces ozone. Ozone is an irritant, O3, and so the irritant effect of smog, and so that reaches a peak, right around noon and to evening time, and then you get a decline further on. So this is a case of a synergetic effect of multiple pollutants in the presence of chemical solar energy. Yes.
I've learned about hazes before, which I think is like when sulfates mix with water. Is that like specifically different from smog, or does smog also cover that?
I would say that a haze is a type of smog.
Okay, and that's with sulfates, not sulfides, right?
I'm not sure that I'm not familiar with that distinction. So I'm not sure how haze is being used in the context that you're mentioning it. But, the important thing is that hazes and smogs, these are sort of results of, mixing various air pollutants and then, adding some energy effect, such as, some environmental effects, such as sunlight or inversion that tends to trap them in an area. Okay. All right, just briefly, indoor air pollution is a major problem, and particularly in less developed countries where people rely on solid fuels, biomass, wood or coal for cooking and heating, and particularly where ventilation is poor. And the consequences of indoor air pollution are worst for children and women who spend a lot of time or tend to spend a lot of time, trapped over the fire here. So you can imagine what it would be like to have an open fire in your house, what kind of, soot and smoke that would produce over time. But for many, less developed countries, this is a particular effect and a particular impact. And indoor air pollution, causes a range of impacts. The World Health Organization offers guidelines. And so this is, emissions of 1 kilogram of wood burned per hour in a 40 square cubic meter kitchen. So 40 cubic meters is a relatively small kitchen. You could easily burn 2 pounds of wood over an hour to boil a pot. And these are all of the, the different compounds that can be released. So indoor pollution can be a very serious impact. We also have examples of indoor pollution that kill people whenever we have power outages from hurricanes. What happens when you have a power outage from a hurricane? Well, people bring their charcoal burner inside, and they try to, cook over that, or they try to run their generator inside, with the result that carbon monoxide and other toxins accumulate. And that's sort of one of the toxic effects of hurricanes and loss of electric power. There are also different sources of indoor air pollution caused by the chemicals, the additives that are present in different kinds of household products. Asbestos, pipe insulation. There have been instances in the past where drywall and plywoods have been produced with compounds that leach out over time. And again, the impact is not acute, but with the chronic toxicity from prolonged exposure, there can be very serious health effects. All right, I want to keep pressing on to water pollution. I don't know if we're going to have enough time for discussion. Water pollution is a degradation of water quality. Water is considered to be polluted when it's rendered unfit for a specific purpose. Okay, so water might be polluted, by adding a very small amount of, a few drops of gasoline, for example, in a gallon of water would render it unfit for the purpose of drinking. But you could still use that same water to wash your car, or wash your cat, or your dog. So the specific purpose, the degree of pollution depends on the purpose for which you want to use it. And again, the Clean Water Act and the EPA set limits for the concentration of various pollutants in water. And water pollution was one of the first pollutions, or the first examples of where contamination of produced by anthropogenic effects, sewage, produced serious health problems. Access to safe drinking water is the #1 preventable cause of death and illness in the developing world, and it remains a problem in the United States, where giardia, amoebic dysentery, are recorded pretty regularly. I used to live in Galveston, Texas, and every once in a while they would issue a warning, watch out, we've detected giardia in the water supply, and we don't have to run out and boil our water or buy bottled water. So we sort of take clean water for granted in the United States, but in fact, that assumption is less and less active. And so the example of that is can be found in the case of Flint, Michigan. Flint, Michigan hasn't been in the news quite so much, but this is a particular story. So Flint, Michigan, experienced a series of economic problems. The city went bankrupt, and state officials were appointed outside operators to manage the city. In other words, the city went bankrupt, the state took it over and said, okay, well, the mayor and the city council, et cetera, they're not running the city anymore. We're going to appoint these officials. Let's see, the officials came in and said, okay, well, we got to save money. And they decided to get their water directly out of the Flint River instead of the Detroit water facility. Well, right away, they started detecting coliform bacteria, which is a form of bacteria produced by human waste. And that said, okay, we got to control that bacterial contamination of the Flint River water. And so they added chlorine to the water in greater and greater amounts to try to reduce the numbers of bacteria that were present. That was fine. It controlled the amount of pollution of bacteria that was present. However, the presence of this chlorine began to cause effects on pipes. And so the pipes started corroding the extra chlorine in the water that they put in to add to control the chloroform bacteria, started eroding the pipes. And most of the pipes were steel, but they had lead joints. So the places where the pipes came together were sealed with lead solder, and that lead began decomposing and leaching into the water supply, and that caused lead poisoning. The existence of this lead poisoning and the occurrence of this lead poisoning was denied for years by these officials. And it wasn't until there was a pretty heroic doctor who said she was looking at the occurrence of lead pollution and looking at the occurrence of pathological effects among children, and she realized that she was seeing much higher than normal occurrences of developmental and other problems in young children, and she related that back to the occurrence of lead in the water. And this whole sorry story eventually unraveled. And to this day, the people of Flint have not had the funds or the wherewithal to replace their pipe, and they're able to use the water for certain purposes, cleaning, flushing toilets, and so forth. But drinking water, has to be obtained from commercial sources. Here's an example of sort of knock-on effects that are producing let's see. I think I'm going to stop right there. I've got a couple of more slides about biological oxygen demand and so forth. Let me just talk about biological oxygen demand a little bit, because that's something that will come up again when we're looking at coastal pollution. So biological oxygen demand is the amount of oxygen that's required for bacterial decomposition of organic matter in water. So, this is a very familiar equation. We're using oxygen to oxidize organic compounds. Bacteria are doing that. So if bacteria want to consume organic compounds out of the water, they have to have oxygen to do so. If you dump more organic material into the water than is resupplied by the oxygen that's removed, the biological oxygen demand can deoxygenate the water. And so, here's an example of a sewage treatment plant, which is dumping a slug of organic material into the water. The biological oxygen demand then increases because the bacteria are breaking down this organic compound, and the dissolved oxygen goes down. So within this polluted zone, there is the effect of hypoxia, or, well, usually it's hypoxia, low oxygen demand. So this low oxygen concentration means that aquatic organisms that need oxygen for survival don't have and can't absorb enough oxygen out of the water. And so this can produce dead zones within rivers. We also get dead zones off the coast of Louisiana and Mississippi on an annual basis because of organic material produced from excess nitrogen fertilizer. Okay, well, I'm going to open the breakout sessions, and I'll keep them open until 1:15. Let's see, stop sharing. And I just want you to make sure that you all understand the concept of externalities in the breakout room, and to come up with examples of positive and negative externalities. So I guess I didn't show this. Let's see. So an externality is something, I think that we already talked about this, but an externality is something that, while it does not monetarily affect the producer of a good, does influence the standard of living of society as a whole. So a classic example of an externality is the smoke emitted by a power plant, okay? So a power plant, in burning the fuel that it needs to generate electricity, which it sells to earn a profit, it produces this waste product, the smoke. It has to, as part of its cost, it has to somehow get rid of that material because otherwise it would accumulate, or because the natural process of generating electricity produces this compound. Well, if it just releases this into its air, it's getting a benefit. It's able to produce this waste product without paying the cost of cleaning it up. Well, the externality, the negative externality, comes in for the people who breathe that material in and suffer a lower quality of life, or even morbidity or mortality as a result of the pollution produced by the power plant. So that's a classic externality example. And I'd like you to think about, in your groups and the time that you have, make sure that you understand this. What are some examples of negative externality for air, water, and climate? And can you compare and contrast, pollution with pandemic effects? So let me just open up and take a few minutes to briefly discuss this, and then we'll get back together at in about 5 minutes, and you can do all that. Okay. So Carolina, where do I put you?
The Planeteers.
Planeteers. So you won't be in there long. Carrie, why don't you go to the Wayfinders? Taryn, you go to Aquatic Junkies, right?
Yes, sir.
Delia is Planeteers as well.
Planeteers. Kate, Cabbage Patch.
Team title.
Team title, huh? Catherine, Cabbage Patch, right?
I'm in team title.
You're in team title too, okay. Whitney, you're in Cabbage Patch, right?
No, Green Machine.
Green Machine. I better write this down.